Hey friends! We're going to talk about the Galton Board and probability. So the Galton Board is a really good visual tool to demonstrate, normal distribution and ratios and probability and stuff like that. So we often say, well, how likely is that to happen about different things? It could be, how likely is it for your favorite team to go to the World Series or the Super Bowl? The kittens think it's romper room time. Oh my goodness. Okay. So, to go to the Super Bowl or something like that. How likely are you to... Oh goodness, let's see. How likely is it to rain 7 days in a row over a certain period of time? When people are talking about how likely something is to happen, they have to gather a bunch of data and they have to look at that data and figure out the probability. Probability, likeliness, same thing. So Galton's board will help us do that. There are 3,000 little beads down here, if you can see them. There we go. 3,000 little beads are down inside that little chamber. If I was to take one bead and drop it, okay, which if I turn this over, all the beads will drop. But if I was to take one bead and drop it, how likely would it be to land in any one of these 28 chambers? So I'm not sure if you can see that, but there are 28 individual chambers down here, separated by pieces of plastic. Okay, so dropping one bead down below, there would be a 1 in 28 chance that it would land in this one, or this one, or this one, or this one, or this one. A 1 in 28 chance because it's 1 out of 28. All right, so if you take that, there's not a lot that you can count on when you're just dropping one bead and letting it make its way. So if you've ever seen Plinko on The Price is Right, or we've done Plinko at our community days for review, you drop the little disc and it ding, 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 and it goes down to one of the slots down below. It's hard to guess or predict or figure out what the probability is for the disc or the ball to land in any specific chamber. But if you repeat the test over and over and over a large number of cycles or a large number of tests, then you're going to start to see a pattern develop. So that's what the Galton board is going to show you. Instead of dropping one ball, we're going to drop 3,000 balls and let the test repeat itself 3,000 times in a very short period of time. And what do we notice? We notice that most of the balls hit in this upper curved area. There's a larger amount of balls that have fallen in these chambers than in the chambers over to the sides. That may help it be seen better. Okay? So, doing that one time does not give us an assurance of the pattern. That's just a possibly it was a random outcome. But we can see that it does follow this curve that is superimposed on the plastic. So let's just tip it over. We're going to let them all drop down again. Okay, now we're going to try it again. So we want to make sure that it's level, and let me hold it like this. It's not a magic trick or anything like that. It's just the path that the balls are taking. And we'll watch again and see what happens. So once again, most of the balls are in the center chambers. One did go a little bit higher this time, but for the most part, they are following this curve. Okay? So let's try it a few more times just to see if we get the same outcome over and over again. Okay, so we have very few over to the side and more and more and more as we get toward the center. Okay, let's try again. Okay, so let's talk about it a little bit. When we were dropping one ball at a time, if we could drop one ball at a time, we would have a 1 in 28 chance that it would land in any one of these. But this is showing us a different thing. It's showing us that there seems to be more probability, there is more probability that it's going to land in these center chambers than it is to land on these outer chambers. Why is that? Why is that? So that's where Pascal's triangle comes in. So I'm going to read that to you real quick. Okay, Pascal's triangle. Let's see if, oh my word. Okay, we got to turn it upside down so you can see the numbers on there. Okay, so Pascal's triangle, if we can get it to focus. It may not work. So you have a triangle with these honeycomb shapes here, and you've got numbers down, and I'm not sure that you're going to be able to read that, but Pascal's triangle is a triangle of numbers that follow the rule of adding the two numbers above to get the number below. So the number in this top honeycomb is 1. There's 1 here. Then if you go down, you have 1 plus nothing is 1, and 1 plus nothing is 1. Then we go down to the next row, and we have on diagonals 1 here plus nothing is still 1. And 2 plus 1 is 3, and 3. Okay. Yeah, it's still hard to see. All right, so I will continue. This pattern can continue endlessly. Blaise Pascal, 1623 to 1662, used the triangle to study probability theory. As described in his mathematical treatise, Trait du Triangle Arithmétique, 1665. Other mathematicians studied the triangle centuries before Pascal in India, Persia, China, Germany, and Italy. The triangle's patterns translate to mathematical properties of the binomial coefficients. There's also not just Pascal's triangle is involved here. We have Fibonacci's numbers. Okay, Fibonacci numbers. The sum of the numbers on the diagonal shown on Pascal's triangle match the Fibonacci numbers. The sequence progresses in this order. So that's these tiny numbers that you can barely see. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. Each number in the sequence is the sum of the previous two numbers. So 1 plus 1 is 2, so it's 1, 1, 2. Well, 1 plus 2, 1 of the second row, plus 2 of the third row equals 3. Then the 2 and the 3 equal 5, and so on and so on and so on. Leonardo Fibonacci popularized these numbers in his book Liber Abaci, 1202. A Fibonacci spiral is a series of 1/4 circles drawn inside a pattern of squares with Fibonacci numbers for dimensions. That's not actually used in here, but we have the Pascal's triangle and the Fibonacci numbers. The reason that these are used here is to determine when a ball drops, how many directions, how many options it is, what the probability is that it's going to go to that direction. Well, there's a 1 here on the top. There's only one place that this could come from the chute, right? One place is going to hit this honeycomb here. Then the next are also 1s. It could only come from here, one place to here, because nothing's going to shoot from this direction, and one place from here because nothing's going to come from this direction, because there was only 2 ways for this post. If a bead hits this top post, it's going to go left or right. Okay. From this particular post, it's going to go left or right. Even if it goes left or right, forgive me because I'm not sure if it's translating the same direction, it's going to hit onto this post. It's not going to go over to this post or this post over here, which means there's only one place that these are going to come from. Then you have another one on this far hand, because again, if it's coming from here, but it's not going to be coming from out here, it only has one place that it's going to come from. This middle one could come from this or this, which would make it a 2. And this one is the same as the far one over here. It's only going to have one direction it could be coming from. And it translates down and down and down. All of the outside honeycombs have a 1. It means that there's only one route that it could fall from to land in these. However, when you get further down on the inner tracks, so we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So that means there's 3 different places. I really should have something to point with. There's going to be 3 different places that it could come in from, 3 different routes that it could be coming in from for these 3 honeycombs right here. When you move down to the next row, you still have one on the outside, but it's 4, 6, 4. 4 different routes could come to this honeycomb. 6 different routes could come to this honeycomb. 4 different routes to this honeycomb. I'm not on the right one. It should be 4, 6, 4, sorry. Then we go down one, and it's 5, 10, 10, 5. So you can see that these inner chambers, these inner honeycombs just keep expounding, and bigger routes can send them to these honeycombs, which raises the probability of the inner chambers. With these all staying 1, 1, 1, 1, 1, 1, 1, 1, out here, sorry, on these, it is a slim chance that the beads are going to go into these outward chambers, because only one route is going to take it there. But the numbers that exist in the center down here are, for your very, very bottom row, let me get back up there. Your very bottom row are 1, 11, 55, 165, 330, 462, 462. So these inner ones have 462 more chance of getting hit with a ball at the bottom row than this one. 1 chance, 462 chances. And then we go back to 330, 165, 55, 11, and 1. So the chance of these 2 inner ones at the peak up here, even though it didn't happen exactly that time, these 2 inner columns have 462 more chances, more probability of having a ball go down into them than the outside honeycombs and chambers do once it shoots out that direction. So when you take that and you multiply it over 3,000 beads, that one worked out pretty great. Okay, so it really does follow that curvature. So the curvature is a bell curve or a bell histograph, and it is also called normal distribution. Let's see. I'll just go ahead and read that to you. The normal distribution, often referred to as the bell curve, is the most widely known and used of all probability distributions. Because the normal distribution approximates many natural phenomena so well, it has developed into a standard of reference for numerous probability problems. Several sets of data follow the normal distribution. For example, heights of adults. If you took 1,000 adults or 3,000 adults and you took all of their heights, then you would get a mean, which I'm not sure if you can see that there is a line that falls right here. It's kind of a goldish line, and that would be the mean. Once you took all of the adults' heights. Okay, let's see. The weight of babies, classroom test scores, returns of the stock market, and beads in the Galton Board. So you have the average or the mean on the center here. And as you can see, time after time after time, most of the time, they are going to fall around the average or the mean. That's why we have average height, average weight, and we scale things off of that. So I will, let's see. As demonstrated by the Galton Board, the random path of 3,000 beads approximates a bell curve every time. The standard deviation is a measure of how closely all of the data points are gathered around the average. The shape of a normal distribution is determined by the average and the standard deviation. The more narrow the bell curve, the smaller the standard deviation. When the bell curve is wide, the standard deviation is large. So one thing that we could talk about for this one is we talked about height. Okay, so we could talk about the average height of a newborn baby versus the average height of a full-grown adult. So most babies are between 19 and 21 inches long at birth. So you're talking about a small margin of difference there, 19 to 21. If we were measuring babies and we had the standard or the average or the mean of them, this bell curve would be more of a spike because it's a smaller difference between the lowest and the highest. Average for babies, 19 to 21 inches. But full-grown adults can be 5 feet tall or even shorter, or they could be 7 foot something. So the curve of a full-grown adult study is going to be a broader, wider curve than if it was a newborn study, which would be a higher, sharper curve that would be shorter here. And most of them would still fall in the center, no matter what you're doing, full-grown adults or newborn babies. But the curve would be sharper because it's a smaller, closer set of numbers. And I'm looking here, let's see. As seen in the graphic, about 2/3 of the data in a bell curve fall within 1 standard deviation of the average. About 95% of the data falls within 2 standard deviations and 99.7 within 3. So what they're saying is that if you look at this, all but 0.3% falls within the first 3 columns. 1, 2, 3 parts away from that standard, average, or mean. So that is the Galton Board, and there's much, much better explanations on the internet all about it, about Pascal's triangle and the Fibonacci numbers and everything. But it'll be fun just to play with it and have them hypothesize, dropping one in where it would go, and we don't even have to let them see like this to begin with. You could just say, I have 3,000 beads and I have 28 chambers. What's the probability of the balls making it into which chamber? What's your hypothesis? And then we could go ahead and turn it and reveal that it seems to follow this pattern on here. And you can repeat and repeat and repeat and have them make another hypothesis. And then for however old or young they are, you can explain some of that. But honestly, we could keep it as basic as, what's the probability that any of these 3,000 beads is going to fall into any of these chambers? Does anybody have a guess? Are they going to be equal? They're all going to hit different pegs. They're going to work their way down. And what's the chances that there's going to be a pattern or a lack of a pattern or anything like that? So then we turn it over. We let them come down and we say, that's interesting. It seems to follow this design here. That's weird. Let's try it again. So we let them all go down, make sure they're in there. Try it again. It did it again. It's following that curve. That's really odd. Or is it? Let's try it again. It did it again. There must be a reason for it. And then we can just talk about how there's pegs here and it forces the ball to go one way or another. And the fact that it has to go left or right. And a lot of these are in the center, but not very many are out on the sides. Well, let's talk about how did it get out to the side? It would have had to go that direction multiple times. So what's the chance that the ball would continually choose the same direction each and every time? Well, it looks like it's a very low probability that it would choose the same direction almost every time or every time versus working its way back and forth to where it doesn't really get off track from where it came out. Right here, it's pretty much staying within that same section. The probability is very high that they will go towards the center, and the probability is very low that they would come out to the side. And we're going to talk about probability. And we're going to mention that God is 100% certain and faithful all of the time. But everything else has a degree of chance, even within a normal distribution or a bell curve, because you will see that sometimes they go above or below a little bit from where the bell curve's line is at. So again, only God is always 100% faithful and certain.